So, I was reading about this very interesting statement called Sperner's lemma.
Sperner's lemma, what's that?
It's actually, it has a nice name, but it's actually about, putting colorful balls on a triangle and seeing how many different colorful triangles you can make.
Sounds fascinating. Tell me more.
Yeah, so here's what you do. You sort of take a triangular, let's say, board with little holes to put different colored balls in them. Okay, so here's a board. Let's see what we can do.
So I have a board here.
Yeah.
And how many colors are we using?
So we have to use 3 colors. So let's say we use red, yellow and blue.
Okay, fine. So I have this triangle and the 3 corners, I put different colors?
You put different colors, one each on each of the corners. Now what you have to do is to fill the other holes also with balls of these 3 colors.
Okay, so can I put a yellow ball here? Can I put a yellow ball here?
Okay, not quite. So what you have to do is on that side which connects the red with the blue, you can only put either a red ball or a blue ball in all those holes, but you can do it any way you want.
Okay, so say I put some red balls and some blue balls.
Right.
What about this edge?
There you put red and yellow.
Okay,
any
so
way you like.
any way I like. So I can just put like a yellow,
Right.
something like that.
Yes, and on the third side you put blue and yellow.
Okay, so let me just put something like this.
Right. And now you have a few holes in the insides. There you can do whatever you want. So just put whatever color.
So let me just put some random colors over here.
Right. Okay.
Okay. So what's Sperner's lemma now?
Right. So now of course there are many different ways of doing it. You did it one way, but Sperner's lemma says no matter how you do it, as long as you satisfied the conditions that I told you about initially.
So those are that the 3 corners must have different colors.
Right.
And each outer edge must only have the colors of the corners that of the 2 endpoints of that edge. Right. So here it's red and blue. So all these are red or blue.
Correct.
Okay.
Right.
Okay. What does Sperner's lemma say?
So it says that no matter how you arrange these balls, as long as you satisfied the conditions I told you about, which are, if you remember, I need to have.
So the 3 corners have 3 different colors.
Right.
The colors on each outer edge must be the same, one of the colors on the 2 corners that are on that edge.
Right.
Right. So like this is the edge which is red and blue endpoints. So everything in between must be red or blue.
Right.
Here everything in between must be red or yellow, and here everything must be yellow or blue.
Right.
But there is absolutely no conditions on the inner.
Right. There are no conditions
colors.
on the inside colors.
Okay.
Okay. Now what Sperner's lemma says is you now start looking out for what we will call a multicolor triangle. Okay, what's a multicolor triangle? So look at the small triangles now.
Okay, so here's a small triangle
Right.
over here.
And there's one, right, and there are many more like that, as you can see in this whole figure. Do you want to find another one maybe?
Okay, so here's another triangle. So there are many of them.
There are
right?
many of
Okay.
them, right. Now you say that a triangle is a multicolor triangle if the balls on its 3 vertices are of 3 different colors, meaning one red, one yellow and one blue.
Okay, so this triangle here is a multicolor triangle,
Right.
but this one here is not a multicolor.
Is not a multicolor triangle. Okay. Now what Sperner's lemma says is that the total number of multicolor triangles will always be an odd number.
Ah, interesting. So let me see if that holds in this example. So I have here one multicolor triangle. Do I have any other? So this triangle over here is not multicolor because it's blue, blue, red. This one's red, red, yellow.
Right.
Okay, so here we have here's a multicolor triangle, right?
Right.
Okay, so I have 2 multicolor triangles. Now let's see over here. This is not. This is not. This is not. I think I found another multicolor.
Yes,
triangle.
that's right.
Okay, let me look for some more. Here's one more, right?
Right.
And right next to it, there's another one.
Right.
And are there any more? Let's see. I think that's it. So I have here, looks like I have 5 multicolored triangles.
Right, absolutely, and 5 of course is an odd number. In particular, it says that the number of multicolored triangles is at least 1, right?
Right,
Because
if it's odd, it
an
cannot
odd
be
number.
0.
Can't be 0. So it's either 1, 3, 5. In particular, it always exists. So no matter how you put those balls, as long as you obeyed the rules, you will always find at least 1, and in fact you will always find an odd number of such triangles. Okay, so let's just play. Let's try doing the following. Let's try to destroy one of these multicolor triangles that we had. Let's change.
Okay. So say I change. Let's take this triangle over here.
Right.
Okay, I'll destroy it. I'll put a red over here.
Okay.
Okay, so this is gone. So maybe I have an even number of multicolored triangles.
So now you probably have an even number of multicolor triangles. Is that right?
No. See, this one changed. This one became multicolored.
Right. So you destroyed that, but you got another one somewhere else. So you now have an odd number.
Let me try destroying one more. Okay. So let's destroy this one. So this one is red, yellow, blue. So if I make this red, then this multicolored triangle is destroyed.
Right.
And I don't think I've created a new multicolored triangle. So do I have 4 multicolored triangles? Oh look, this triangle which was multicolored earlier is no longer multicolored.
Right. So you destroyed one, but you also ended up destroying another one.
That's interesting. So either I end up destroying 2 or I end up creating one.
Correct, exactly. So no matter what, you'll always find finally an odd number of multicolored triangles.
Let me try one more example. So suppose I destroy this triangle over here. So how can I destroy it? Maybe I can change this red over here to a yellow or a blue. Okay, let's put a yellow here.
Okay.
So now what happened? So that's no longer a multicolored triangle. But I have created a multicolored triangle over here.
Right.
Oh,
Absolutely.
that seems to always work.
Yes. And this also works no matter how big this triangle is. I mean, here we only had 5 balls on each side. You can have 500 balls and it still works the same way.
Fascinating.
So let's recall what Sperner's lemma says. We take a triangular array of dots. We give those dots one of 3 possible colors subject to some rules. First, we have to color the 3 corners using the 3 different colors. Vertices along a boundary edge have to have the same color as one of the 2 endpoints of that edge. And thirdly, the interior vertices can be colored arbitrarily. So let's look at an example. So here's a triangular array with the 3 corners marked. So one of them is blue, and so here's the blue vertex. One of them is red. And one of them is black. Now let's look at what the conditions say. It says along each boundary edge you can give one of 2 colors. So let's say we give this blue and maybe another blue. We make this red. So maybe many more reds. So here are a few more blacks. And now we look at the interior vertices, and there we are free to do whatever we want. So we give, let's say, red, red and black. Okay, so here's one possible coloring which satisfies all the required properties. Now the conclusion of Sperner's lemma is the following. It says if you have a coloring like this, then you can always find a multicolor triangle. In fact, it says the number of multicolor triangles is an odd number. Okay, so let us go back and look at where the multicolor triangles were. So recall a multicolor triangle means the following: it is a triangle in which all three colors appear. So here's an example, one of them is red, one black, one blue. So the three vertices should be three different colors. So such a triangle is what you would call a multicolor triangle. Let us look for the multicolor triangles in this picture. So here's one, here's another red, black, blue, here's another red, blue, black, and here's another one, here's another one. So we found the 5 multicolor triangles, small triangles in this case, and as one can check, there aren't any more. So it is an odd number, and that is what Sperner's lemma concludes. That is the conclusion of the lemma. So let us see what the ideas of the proof are. So the very first thing we will do is to analyze what can happen when one has one of these triangles. So let us look at this triangle here. So here is a triangle, one of these small triangles which we are interested in proving that we can find such multicolor ones. Now given any such triangle, there are sort of 3 faces, right. So there are 3 ways of sort of, if you imagine you are in the middle of this triangle, there are 3 ways of exiting this triangle, okay, of going out of this triangle. So here are these 3 possible directions through which you can sort of move to the adjacent triangle. So imagine these are sort of, it is a triangular shaped room and there are sort of 3 doors or 3 walls, and you can imagine going out through one of these 3 doors into the adjacent room. Okay, so that's the basic structure we will use. So we keep doing this to each of these rooms. So here's the next room, and the next and the next and so on. So when we connect all these rooms up using these sorts of paths, this kind of thing we will call a skeleton. So let us form the skeleton of the triangular array. Okay. So what does that look like? So in this case, these were the 3 vertices. Then for this entire triangular array that they enclose, the skeleton is now this. So I am just connecting up each triangle with the center of its adjacent triangle. Okay, and that's almost done. So that's it, I guess, because the outer triangle that we are looking at is really this one here, the one which connects these original 3 vertices. So if I give you a triangular array, what I first form is the skeleton of the triangular array. So we will go back and try and draw the skeleton for this configuration of balls, but now we will not draw sort of every single edge of the skeleton. Let us pick 2 of our favorite colors. So let us say that red and blue are going to be our favorite colors. So we will choose red and blue, and we will only draw the skeleton for those edges of the triangle which have one red and one blue on them. So if I have a triangle like this, then I will only draw this single edge of the skeleton. Okay. So let us see what the skeleton will look like in this case. So here is a red and a blue edge. So I will just draw this line, the skeleton through them. Here is another red blue. So I draw this red blue. Here is another red blue. Here is another red blue, and that is it. Okay. So what I have just now drawn is only the skeleton for edges which have one red and one blue in them. Okay, so it does not look particularly interesting in this example. So why are we doing this in general? So let us try and analyze what this actually gives us. So if you have a multicolor triangle, for example, so what are the various possibilities? So if I have a triangle with the 3 colors, what will this sort of reduced skeleton look like? So if I have got a red, blue and a black, then there is only one edge which has a red and a blue. So I will in this sort of triangle I will only draw one single edge here which connects this center to the center of the next guy. If I have a triangle in which there are, let us say, 2 blue and 1 red edges, then here I will, well, here is one red blue edge and here is another red blue edge. In this case there is only one of them. So I will draw an edge like this and an edge like this in the skeleton. Okay, and what else can happen? Well, these are more or less the only possibilities. Of course I can have cases where there are no red blues. So maybe I have, say, black red red, in which case for this triangle I do not really draw any edges in the skeleton. Okay. So the observation here is that no matter what the configuration of balls looks like, in any one of these small triangles you can either have 0, so there are 0 edges in the skeleton leaving this triangle. In this case there are 2 edges leaving this triangle or 1 edge leaving this triangle. Okay. So there are 0, 1 or 2 possible edges of the skeleton that can leave any given triangle. What cannot happen is the following: you cannot have a triangle with 3 different edges leaving it. So is it possible, let us ask ourselves, if we can find 3 different edges leaving a triangle, can't we look at some colors of balls which will make that happen? So what would this mean? Suppose that did happen, it means that I have got to have a blue here and I have got to have a red on the other side. That is when I draw an edge of the skeleton. Now let us look at this part. I have a red here, which means that this other side must be a blue. Okay. But then if you look at the third edge, I have got a blue with a blue, which means that this thing that I drew here, this last edge, can't actually have been an edge, because that would correspond to having 2 blues on the 2 sides, on the 2 ends. So the thing that you can never ever have is a situation where there are 3 edges of the skeleton leaving a given small triangle. So there are only these 3 possibilities: 0, 1 or 2 edges. Okay, and if it has one edge, then in fact the triangle has to be a multicolor triangle. So this is exactly the case when the small triangle is a multicolor triangle, and in the other 2 cases the triangle can't be a multicolor triangle. Okay, it must have at least 2 repeated colors. Only then can you either have 0 edges leaving it or 2 edges leaving it. So that is really what a multicolor triangle is all about from the point of view of the skeleton. It is exactly all those small triangles which have only one purple edge leaving it. Okay, so that is going to be the idea, that is going to be the key thing. So what we will do is to look at all these different we look at the skeleton, and if you in fact here look at the multicolor triangles that we had found already, here is one triangle and so on, these turn out to be exactly the triangles which have a single edge leaving them. As you can see, there is just a single purple edge which is leaving each of these triangles. So that is exactly how we will find them. Okay, so here is an example of if you look at this small triangle here, this has 2 different edges. So there is one purple edge coming in here and one going out, and that guy is not a multicolor triangle, it has got two reds and 1 blue. Okay, so let us now do this. So this is going to be the idea of the proof. So what we will do is the following: we will draw the skeleton and then observe what that graph looks like. So, where does all this graph theory that we talked about come into play? The skeleton is going to be thought of as a graph. Okay. So, that is the key connection here. The skeleton is going to be a graph. So, this is not that original big skeleton I talked about with 3 edges leaving every triangle. The skeleton that here I am talking about the reduced skeleton, the smaller one, which is only for blue and red. So, this is the blue red skeleton if you wish. Okay, maybe we could even call it that. So, let us call it the red blue skeleton. Okay, so it is going to be a graph. Now, what properties does this graph have? So, that is the first observation. So, what we know about this graph is the following, that property number 1, this graph has, well, how am I going to think of my vertices and edges of this graph? Well, I will think of, for each small triangle, I will think of the center of that small triangle as being a vertex of my graph. So, when I draw a skeleton which looks like this, for example, so I will imagine that the centers of my small triangles are my vertices of the graph, and the edges are of course those edges of the skeleton that I have been drawing. Now, what do we know? We know that each vertex, that is each triangle, can either have two edges leaving it, or one edge leaving it, or 0 edges leaving it. And recall that this is what we had defined as the degree of a vertex. Okay. So, the degrees of the vertices of the skeleton, so let us call this skeleton as S. So, the degrees of the vertices of the skeleton S can only be 0, 1 or 2. There are only 3 possibilities. Okay. So, here is an example, here is a vertex which has degree 2, here is a vertex which has only degree 1, and you can of course have vertices which have degree 0. You could have triangles with maybe all 3 reds on the 3 sides, and those would have they would have degree 0. Okay. So, that is the first observation. Now, the second observation pertains to the boundary of this graph. So, let us look at the edges along the boundary of a coloring. Now, what did the boundary look like? So, whenever we colored a boundary, it had to have some blues and reds, for example, right. So, let us look at the red blue boundary. There is always a red blue boundary which has reds and blues. So, let us look at this guy. Now, how many of these edges, these purple edges that I was drawing in the skeleton, how many of them exit this boundary? Okay. Now, when would you have a edge exiting the boundary? Exactly when I have something connecting a blue with a red, right. So, here is a red blue, here is a blue red, and remember I had one condition which said that the 2 ends, the 2 vertices at the ends must be of different colors. So, if I have a red on one side, I must have a blue on the other side, and so what I have in this example are these 3 edges, these 3 purple edges have one red and one blue vertex on the 2 sides. So, when I draw the skeleton, I will draw these these perpendicular lines joining these, and of course the rest of the skeleton could look different. I could have various things going on after that, but I am just looking at what the boundary looks like. Okay. So, on the boundary, what I have in this example are these 3 vertices. So, how many vertices do I get which are outside the boundary, which are these I will call as my external vertices of the skeleton, because they are sort of outside this original triangle that I started out with. So, these are my external vertices of the skeleton. How many external vertices can you have in your skeleton? Okay. The answer, well, we do not know the precise number, but the key observation here is that the number of external vertices is always an odd number. Okay. So, here is a key observation, here is a lemma. The number of external vertices of the red blue skeleton of the skeleton S is always odd. Okay, and the proof is, well, more or less by inspection, it is the same visual idea. What are we doing when we sort of look at the vertices along that edge? Well, when we sort of look from top to bottom, we first see a red, and at the bottom we see a blue. So that those two are given, right, that they are two different colors, one side red and blue, or maybe this is blue and that is red, does not matter. Now when I go from red to blue, as I travel down that edge of my triangle, how many times should the color change, right? So when I go from red to blue, if the color changes once, then the color is changed from red to blue, as in this example. Then going from here to the next dot, the color does not change, I am still at blue. So far color changed once, and now going from this blue to the next red, here the color changed again. So the second time color change and third time color change. So observe that these edges, these purple edges that I have drawn, or the skeleton, whatever you wish, those are exactly the places where the color changed from one color to another as you travel down that edge. So the number of color changes is what we are looking at. So observe the external number of external vertices is also equal to the number of color changes as you go from top to bottom. Top to bottom along that edge. But if you started with red and finally you ended up at blue, the only way that can happen is if you changed color an odd number of times, right. So this is odd, because of the given condition that you started with red and you ended up at blue. Okay, so this is the main observation, that along the ends, along the boundary, the number of external vertices that you have in your skeleton is always an odd number. Okay, so now we are almost ready to finish the proof. So what have we understood about the skeleton? We know that it's this, there is this large triangular array, the original one, and the skeleton is some graph. So this is the red blue skeleton, is going to be some graph. It is going to have some number of external vertices, which is always an odd number. So here is a bunch of external vertices. So I have an odd number of them, and then I do not quite know what happens inside, a bunch of things goes on inside. I have got some edges and so on. So I do not know what the general skeleton looks like, some strange thing, but what I do know is that the total, the degree of every vertex is only one of three possibilities, it is either 0, 1 or 2. Okay, so that is the other important thing. So there is odd here, odd number of these here, and degree is restricted. The degree of any vertex can either be 0, 1 or 2 for every vertex. So it is a very special kind of graph. Now we sort of looked at one very important property of degrees in a graph, and recall this statement now. So this says that the theorem about degrees, that if you add up all the degrees, so the sum of the degrees, sum of all degrees of vertices, sum of degrees of all vertices is always an even number of a graph, is even. In fact, it is equal to 2 times the number of edges. Okay. Now the total sum is even, but observe that the external vertices, these 3 guys, or in general an odd number of them on the outside, they all have degree 1. Okay. So these external vertices all have degree 1. So, what is the total contribution to the sum of degrees by the externals? They contribute an odd number, right, each contributes 1 to the degree and there is an odd number of them. So, the externals contribute, so sum of degrees of external vertices is odd number, and the total sum is even, which means that the sum of the internals, sum of degrees of the internal vertices must be also an odd number, because the total sum is even. Now observe that the degree, however, can only be 0, 1 or 2, right. Recall that was a very important observation. Each vertex can only have degree 0, 1 or 2, but the total sum of all the internal vertices is an odd number. Now how can that happen? This means that the number of internal vertices with degree 1 must be an odd number. So this, from this we conclude that the number of internals because the other two possible degrees are 0 and 2 and they are both even numbers. So the number of internals with degree 1 must be an odd number. Okay, so that is the final conclusion. But then recall again that, you know, when did a vertex have degree 1? So these were the only 3 possibilities, right, for vertex degrees. You can have 0, 1 or 2, and 1 is the only case where you get something multicolor. If a vertex has degree 1, it means that the associated triangle, this one right here, this is a multicolor triangle. That is the only case when you can have degree 1. So that proves Sperner's lemma. So finally we conclude that this implies that the number of multicolor triangles is odd. So that completes the proof of Sperner's lemma.